Hello, welcome to class 2 of the DC circuit or DC controls series of classes. Before we dive into the class, I want to give you a safety tip. I want to talk about how to operate a molded case circuit breaker. Now then, this is a molded case circuit breaker. You probably are very familiar with these. Every house has one. They're throughout office buildings and factory settings. And one of the problems with these guys is there's a certain amount of fault current that they can interrupt or load current that they can interrupt, and occasionally they fail. And so when you're operating these, and it's mounted in a panel board, don't stand right in front of it and do this. Stand off to the side like that, so that if this does fail and there's a large arc flash, you're going to burn your hand, not burn your face. Seems obvious, but you'd be surprised how often that obvious mistake is made. All right. Want to give you a quick rundown on what we're going to be covering today. Oh, that's a sorry little thing. What the hell happened? Clicker just stopped working.
New batteries, or it just doesn't work?
No, there we go. Okay. Now it's working. I don't know why it wasn't working.
No on the whiteboard.
I'll bring it in. I'm going to just practice right now, and it'll be fun to go. Give me about 15-20 minutes to practice, and then we can sit and both learn from the thing to see how it looks and see what post-production we're going to need. So anyway, all right, moving back to this. Okay, introduction. Could you pull that door too? Thanks. Last lecture we introduced some basic logic, just the simple stuff, and or not, that sort of thing. And this time around, what we're going to do is take those basic concepts, and we're going to introduce then the functionality of a circuit breaker and show, using the logic presented in ladder logic in a DC schematic, how a substation circuit breaker works. Okay, but first we're going to introduce a few things that will help you understand better what a circuit breaker is and how it functions within a substation. And for that, we'll be talking about zones of protection. We're going to look at some circuit breaker pictures and really kind of explain some of the more basic things that we do typically in a substation design. Okay, the first thing I want to cover are a couple representations of circuit breakers. On the screen now, there are three ways that we can show circuit breakers in drawings. The first one is really mimicking a molded case circuit breaker, and I don't think that would be terribly appropriate for a substation drawing. The second one is actually mimicking, although it looks similar to the first one, it's actually mimicking an old oil breaker, because in an oil breaker, what you would have is you'd have the bushings up on top, then conductors would come through the bushings into a large tank of oil, and there would be a big plunger in the middle with a huge spring on it, and it looks not entirely different from that depiction, where there's actually two contacts and the thing moves up and down. Anyway, I've always assumed that that is where we got that symbol from. Now the third symbol on the screen, the square, that's what we typically want to use, and most of our clients use that symbol on their drawings. Now then, most importantly is you do want to use the symbol that your client wants to see, but if we are given the choice, then certainly that is the one you want to use. Anyhow, moving next to zones of protection. Now, looking at this picture, hold on. What I want you to see is, boy, that is dark as hell. God darn it. Why is that so flipping dark? Shoot. Oh, that is weird. Okay, what I want you to see in this is this is a one-line depiction of a substation. And you would see that this is 2 rows of breaker and a half. You could also call this a 6-breaker ring bus. And we've got 2 positions off on the side that are transformers and 2 over here that are transmission lines. Now, for the transmission line, this is a circuit breaker, obviously. These are current transformers. Notice you have 2 breakers here, and if you open 2 breakers, you have isolated that transmission line from the rest of the substation. Now, so if there's a fault on that line, your relaying has to trip this breaker and that breaker. Okay, the protective relaying for that transmission line, the current input comes from this CT and this CT. Now similarly, on the protection for this bus, it's coming from this CT and this CT. So the zone of protection for the bus is actually on these breakers, but it really is the CTs that do it. And notice that CTs overlap, so that if you have a bus fault, you're detecting it with these CTs and you trip these breakers. Now then, I want you to think for a moment about what would happen if we were to not connect our CTs that way, not really connect them the right way. Say we put the bus CTs on the outer, or the bus differential on the outer CTs, and the line relaying on the CTs that's adjacent to the line. Now say we did that, and say we had a flashover on that breaker. Well, neither the relaying schemes would see that fault, and you'd have to end up clearing that fault remotely from the other ends of the transmission lines, and that would be a huge disaster. We really don't want to do that. So anyway, this is meant to give you a bit of a depiction, a little bit of an explanation of what zones of protection are. Okay, moving along. Got a couple pictures of circuit breakers here. This is from a substation in Southern California, and this 500 kV, and each one of these devices is a pole in a circuit breaker. So you have A phase, B phase, and C phase. And if you look at this, this is the bushing. So you connect to your conductors up here, and you have disconnect switches out on the far side. You come through some corona rings, this is EHV, then down a bushing, and then into the chamber that holds the interrupter. Now under this cowling, there's our current transformers, and they're the same current transformers I just showed you schematically on the previous slide. In fact, I can show you that. Those CTs right here, oops, meant to go back. Those ones are these. So where you have CTs on either side, and then the breaker in the middle, which really is more than the breaker, it's the interrupter. That stuff is physically located right here. So inside this cylinder is the interrupter, and the insulation medium is SF6 gas. Now, a little thought on SF6 gas. It's a really interesting substance. It's a sulfur hexafluoride. It's a very large gas molecule, or at least it's gas at room temperatures. And it provides us with some really interesting properties. It is an ideal insulating medium. And by ideal, you might think, well, you'd want a perfect insulating medium like vacuum. Well, there's a problem with it. Vacuum is such a good interrupter that as current or as contacts are pulling apart, it actually chops the current. What will happen in most insulation mediums, as in SF6, as the contacts pull apart, you're actually drawing a small arc. Then as you go through a current zero, and we discussed this last week, as you go through current zero, and then you come out of it, the arc simply doesn't reignite, and that's how you interrupt it. And SF6 actually does this perfectly, so it doesn't end up, it doesn't chop the wave, but it also doesn't give you too large of an arc that you reignite, and it doesn't cause excessive wear on the contact. So anyway, it's really a pretty useful substance. Now then, so anyway, these are our, this is 500 kV. Let's look at the next one. This is a 72 kV class circuit breaker. And if you look closely, you're going to see all of the same features. You've got disconnect switches on either side of the breakers, although you can't really see them in this picture. But you have 3 different poles. You can see the outside phase right here, and the interrupter is inside that cylinder. You have 2 bushings, and there's cowlings under which you'll find the current transformers. Now then, if you also look at this, you're going to see right over here, that is the control cabinet. Now, most of the stuff that we're going to be talking about later in today's class, you're going to find inside that control cabinet. And I bring this up because what I really want you to do is keep track of where all this stuff is. So is it in the control cabinet? Is it somewhere else? Is it in the control building? Where are physically each of these devices? Because although we show them schematically, they actually exist. They're physical devices. They have a physical presence. So anyway, let's go ahead and look at a couple more circuit breakers. This is actually the same substation, a different voltage class, and this is a 230 kV. And you see disconnect switches on either side. There's your control cabinet. There's the cylinder that has the interrupters in it. Here are your bushings. And there's the cowling under which you'll find all of your current transformers. Now then, here's kind of an interesting little thing. This is in Southern California. And notice this little standoff bar here that comes off the bushing, so that they're putting their jumpers onto it rather than right onto the thing, or onto the end of the bushing. And here's my question for you. Why would someone do that? Well, in Southern California, you've heard of acid rain. They actually have acid fog. Fog with a pH down around 2 or 3. And what will happen if they didn't do this, as you get condensation on the jumpers, they'll actually drip down and get right onto the bushings, and then you'll have a little streak of conductive water during foggy nights, and it causes flashovers. So by doing that little bushing fitting, fitting on the bushings, you don't have that, and the little drips drop right off, and it keeps them out of having that problem. Anyhow, I think it's rather ingenious, and just one of those little things that all of our clients have, just have different things that makes that are important to them in their designs. Anyhow, the way bushings, the way transform or circuit breakers like this work is there's a mechanical connection between the 3 poles. Now, and the way that there's actually a bar that connects them between them, and then somewhere within that mechanism there's a spring. And off to the side in the substation that day, there was a breaker that for some reason was out of service, and it's kind of an interesting thing to look at. This bar that we're showing here is the thing that rotates and connects between the 3 poles. This is the spring mechanism. And what these things are, it's actually really interesting. I wish I had a Belleville washer to show you. But what a Belleville washer is a washer that's concave. And the idea is that you bolt it down, it flattens out, and it keeps the bolt on it from unscrewing. Well, in these things, think of them as large Belleville washers that are concave, and they put them opposite sides. So when they charge the spring, this motor goes and squeezes it down. And what it allows the breaker to do is have stored energy, which breaker needs for its operations, and do it in a very compact and controlled fashion. Now, older circuit breakers have done this in other ways. Compressed gas was a common one, various spring mechanisms. But this is the method that people have pretty well standardized on. And it's really efficient. It actually works amazingly well. So anyway, if you go and look closely at that shaft, you'll see caution rotating shaft. So that's the thing that when you go to trip the breaker is going to move. And what actually happens is there's a little plunger that goes through a solenoid, and it then, when you trip the trip coil, you run current through that solenoid, and it pulls that little plunger up, and it then releases the mechanism, and it twists and opens your circuit breaker. Anyway, a fascinating device, and I'm sure through the course of your career you'll become very familiar with this thing. Anyhow, I want you to now go to this drawing. It's one of the handouts that you should have in your package and that you had for this presentation. Now, this is an outline drawing for a circuit breaker. Really kind of an interesting thing. And you'll always have one of these with a circuit breaker, and there's a lot of interesting information that you need for both the physical design of the circuit breaker, but also the wiring of it too. I'll show you what I mean. The first drawing up here in the upper left corner is looking down on the breaker, and you'll see 6 bushings. And you identify the bushings with a number. That number it corresponds to or is part of the naming convention of the current transformers that are underneath each of these cowlings around here. So anyway, really important to know that, and the point of reference is your control cabinet. You always got to know when you're doing the wiring where the control cabinet is, because again, that's going to define how your CTs are wired. Now, moving across the drawing, you're going to get some information up in this corner about how to design your foundation. And my recommendation on this is to put a slab of concrete down and then epoxy anchor in the anchor bolts. It's really difficult when they're spaced out that far to get all of your anchor bolts in correctly. And if you try to, I guarantee you're going to have a few of them where they don't end up in the right place. They got to cut them off, and you're going to have to epoxy them in anyway. So you may as well not fight it and just go that way. All right, moving on down to the lower left. This is a view of the circuit breaker from the front. Again, you can see the control cabinet and quite a few features therein. And then you also have a side view here, and it shows how much space you need to have in front of the control cabinet. But it also shows a couple other things. This dimension over here is the amount of free space that you have to get the interrupter out of the circuit breaker if you have to replace it or do maintenance on it. This height above is the amount of room that you need clear to be able to lift a bushing out. And, just who knows, maybe over the course of the life of the breaker, a bushing will fail and you'll have to replace the thing. A point on this, realize that you're probably going to need more clear space above it than just this, because the bushings are a little bit heavy and you probably need some sort of a crane or lifting mechanism. Anyhow, moving along, a drawing like this will always be in the drawing package for a circuit breaker. Every time guarantee it's got to be there. Another thing that you will see is the control schematics, and this is the main one. It shows quite a lot of good features in it, and we're going to spend a lot of time talking about this very drawing. Now then, if you'll notice in this picture, in this drawing, we've got ladder logic format. So there's a positive DC bus and a negative DC bus shown. And then the various connections between the two go through various contacts and coils and other gizmos and gadgets. And that's how we execute the logic that actually makes the circuit breaker work. Now again, it's presented in ladder logic format. You'll see the DC buses that we have. And you also have, by the way, AC buses. You can use AC for a number of different functions, including control voltage. And you'll see that down in this corner where we have some heaters. Anyhow, I have a question for you. I want you to set the drawings aside for a moment. And I want to ask you what would happen if we go and I go home, I want to watch a football game on television, and I'm not, and those that know me can can testify to this, I'm not always the most impatient person in the world. And so I go home and I want to turn my TV on and the TV's dead. Can't get anything. And unbeknownst to me, someone has taken a paper clip, folded it out, or opened it up, folded it over, and jammed it into one of the wall outlets in my house. And it's on the same circuit as my television. So there's, in effect, a bolted fault. But I don't know that. And I'm impatient. So I go home, or I go into and I find the AC panel in my house. I find the particular circuit breaker that is for that circuit, and I see it's tripped, and I close it, and I hold it in the closed position with my finger. What happens? Okay, when I ask this question, I get a lot of funny comments and funny looks from people. And a lot of people, without thinking too much about it, will say, well, you're going to burn something up. You're going to burn up the paperclip, maybe the wire. And then some people will say, well, no, that won't happen. A circuit breaker upstream will trip to clear that fault. Well, that's not correct either. What actually happens is the circuit breaker still trips even though I try to close it, hold it in the closed position. This is a property of circuit breakers known as being trip-free. And if a breaker is not trip-free, it's not a circuit breaker. This is a really fundamental property of circuit breakers. You always have to have them. From this humble little $2 molded case circuit breaker all the way up to all those ones that I showed you going up all the way to 500 kV. They have the exact same property. Now, the way they accomplish it is considerably different. Obviously, I mean, how this thing works and how one of those large circuit breakers works, it isn't going to be the same. But it's still as vitally important that we have this property. I'm going to spend most of the rest of this class talking about this and making sure that you understand how we accomplish this. So for closed logic, again, to accomplish the trip-free concept, what we're going to want to do is mostly shown in this portion of the drawing. That's the closed circuit. There's a closed coil there, and there's a scheme that the trip-free scheme is also known as anti-pumping scheme. And what would be in pumping, or why it's called anti-pumping, think about this, that you have a circuit breaker where someone has tried to trip it and close it at the same time. You're holding those both closed. What you want to avoid doing is pumping your circuit breaker when you trip, close, trip, close, trip, close. Because if you do that, eventually, I mean, you're going to wreak havoc on the electrical system, and you're eventually going to damage something in the circuit breaker, and it's going to stop working. So anyway, we want to make sure that we're covering that and seeing how we are able to control that system. All right, the first thing I want you to do is to look at, I'm going to actually get out of something here. I want you to look at, oh, I see why I did that wrong. Okay, it's this leg of the, this is the leg that's the closed coil, or closed circuit. This is the closed coil. Now remember, the coil is just a little solenoid, and when you run current through there, it creates a magnetic field that causes that little plunger to pull up, and then that disengages the stop that's holding that shaft that we saw in the package, or in the picture, and then it shifts and the breaker opens. The whole thing accomplishes its purpose. Now then, there are many reasons that we don't want to close a circuit breaker. And among them, you'll find them in here. First off, I need to talk ANSI numbering. Damn it. Ah, crap. I got it. Okay, I'm done.